Welcome to The Explainer. Today we're taking a calm, analytical look at what is, honestly, one of the most remarkable athletic achievements in sports history, Ilia Malinin's Quadruple Axel. When you watch this jump happen in real time, people love to describe it as a physics-defying miracle. But today, we're going to break it down not as magic, but as a meticulously engineered, totally repeatable system. We'll look at the exact kinematics that made this possible, and we'll see how it actually operates perfectly within the strict laws of physics. So whether you're a diehard figure skating fan who's followed the sport for decades or just a sports science nerd fascinated by human biomechanics, this breakdown is going to completely change how you watch the sport. Let's dive right in.
Here is the central question that's going to guide our whole investigation today. What actually had to change to make the transition from a triple axel to a quadruple axel possible? For decades, this exact question literally baffled the greatest coaches and biomechanics experts in the world. To really answer this, we need to move past all the hype and look directly at the hard biomechanical data. We've got to understand the precise relationship between height, speed, and rotation that finally cracked the code.
Section 1. The structure of the axle.
All right, so out of the 6 recognized figure skating jumps, the axle stands completely alone. Why? Because it is the absolute only one that takes off with the skater facing forward. But as you know, the rules of the sport and, well, the physics of gliding on ice dictate that the skater still has to land gliding backward on one foot. Because of this incredibly difficult forward takeoff and backward landing, the quadruple axel isn't just 4 spins in the air. It's conventionally classified as a staggering 4.5 revolution jump. And honestly, that extra half rotation is exactly what has made the axle the most feared and respected jump in the entire discipline.
But here is a super crucial, really fascinating detail to keep in mind as we start crunching the numbers. The skater doesn't actually complete all 4.5 rotations entirely in the air. The rotational motion actually begins on the ice, right during the takeoff skid. Think of the skate blade essentially acting like a high-powered brake. That edge aggressively blocks horizontal speed and creates a pivot point. That sudden, violent deceleration converts linear momentum directly into angular momentum. So the twisting rotational speed actually initiates before the skater completely leaves the ice. It's just an incredible display of physics happening in the blink of an eye.
Section 2. Separating history from measurement.
Okay, it's absolutely vital that we don't mix up the timeline here. On September 14, 2022, Ilia Malinin made history by landing the first officially ratified quadruple axel in competition, securing a Guinness World Record. However, the scientific measurements we're examining today, they don't come from that 2022 event. Instead, they come from a separate, successful quadruple axel performed at the 2023 World Championships. We are isolating this specific 2023 performance because that is exactly where the kinematic tracking data was formally recorded by the iScope tracking system. This system uses high-speed cameras and complex software to capture exact metrics. For sports scientists, this 2023 data is precious because it completely replaces our naked eye estimates with hard, incontrovertible physics data.
Section 3. Key data from the 2023 quadruple axel. 8.4 meters. This number is the maximum vertical height Malinin achieved during this specific quadruple axel attempt. It is a staggering amount of elevation, especially when you consider how much rotational energy is being generated at the exact same time. To put that into real-world perspective, 0.84 meters is nearly a full yard of vertical clearance off the ice. Just imagine jumping completely over an average-sized kitchen counter, but doing it while launching off the outside edge of a steel blade that's mere millimeters wide. Wild, right?
But we have to remember, that height doesn't exist in a vacuum. Let's look at all 3 primary values measured along the jump's trajectory. Alongside that 0.84 meter vertical height, Malinin carried a massive takeoff speed of 7.29 meters per second, and that immense speed allowed him to travel a horizontal distance of 2.96 meters across the ice. Let that sink in for a second. 2.96 meters. That is nearly 10 feet of lateral travel. We're talking about the length of a small car. He didn't just go straight up to complete his 4.5 rotations. He maintained incredible forward momentum while elevating over that massive distance.
Section 4. Comparison with the triple axel.
This table compares Malinin's 4A from the free skate to his own successful 3A from the short program at the exact same 2023 World Championships. You can clearly see the massive leaps across the board here. For his 3A, his height was 0.71 meters. For the 4A, boom, it jumps up to 0.84. Check out the dramatic leap in entry speed, accelerating from 6.23 to 7.29 meters per second, and look at the ice coverage, stretching from 2.37 to 2.96 meters. To get that extra rotation and a half, the mathematics essentially demanded significantly more vertical elevation, significantly faster entry speed, and much greater total distance.
Let's focus specifically on vertical height for a moment, because this completely busts some older biomechanical myths. Historically, a lot of coaches and researchers thought skaters wouldn't necessarily jump much higher for quads than triples. The assumption was, hey, they'll just pull in tighter and spin faster. But this chart shows a completely different reality. The average height of 24 world-class triple axels at this specific competition was 0.62 meters. Malinin's own triple axel was 0.71 meters. But for the quadruple axel, he pushed that vertical height all the way up to 0.84 meters. He actively adopted a new strategy to drastically increase jump height to master this element, completely shattering those old assumptions.
Section 5. Interpreting the data. Now, we absolutely cannot oversimplify this. A false assumption would be to look at this data and say, got it, to land a quadruple axel, you just need to jump exactly 0.84 meters high. Let's be very clear. That 0.84 meter mark is not a universal formula, and it's definitely not a guaranteed predictor of landing success for every skater. Rather, it represents Malinin's unique kinematic strategy for this one successful performance. The actual strategy demonstrated here isn't just about jumping higher. It's the incredibly demanding ability to maintain sufficient height to secure necessary rotational time while simultaneously preserving substantial forward speed. This means for future generations of skaters watching this, there is no magic cheat code height. It is an unbelievably delicate balancing act.
Section 6. Conclusion. So what are we really observing here? It's not a single miraculous variable, but a highly complex, integrated system. The transition from a triple to a quadruple axel required Malinin to flawlessly synchronize vertical height, forward speed, horizontal travel distance, and extreme rotational control. It's basically a giant, high-stakes puzzle of physics. If any one of these variables is off, say you sacrifice speed to gain height, or you sacrifice height to spin faster over that nearly 3-meter distance, the entire physics equation breaks down and the system fails. Everything has to work in perfect harmony.
The essence of the quadruple axel was not one extraordinary number, but the precise combination of height, speed, and rotational control working together at the same time. And honestly, if 4.5 rotations are mathematically possible with this integrated system, it leaves us with one incredibly exciting question. What are the true limits of human flight on ice? Thanks so much for joining me for this explainer.